So here we are with assignment 1, part B, question 2, part B, where basically what's happened is switch 1, after the switch was moved from switch 2 to switch 1 for an indefinite amount of time, such as T star, the current actually stabilized. So, and then it was moved back to 2 in part B. So basically, after the current was stabilized for a certain amount of time as T star, it was then moved to 2. The switch was then moved to 2. So now, if you notice, IT is confined to the second loop over here. So you can practically ignore this right now. So now the equation of IT is practically the same, except that there's no real voltage source. So Vs is actually equal to 0. So we can go ahead and rewrite the differential equation such as 0 is equal to VR plus VL, and now we can make those same substitutions that we did in the previous part of this question, where VR is equal to IR and VL is equal to L over DI over DT. Now just to note, we do have an initial equation for this, initial condition for this equation, where I at T star is equal to Vs over R. This initial equation is actually derived from the first part of this question. If you noticed, we did take the limit of t approaches infinity, where t will then stabilize to a current equal to Vs over R. So in this case, we're waiting till T star, where we then move the switch from 1 to 2, such that the current has stabilized at Vs over R. So this is our initial condition. We just need to keep that in mind for later on. What we can go ahead and do now is substitute these two in here. So you get a 0 is equal to IR plus L di over dt. Take the IR to the other side, is equal to L di over dt. And now it's a basic separable equation where you can just multiply both sides by dt and divide both sides by I and L, so you can get your L to the other side, I to one side, and dt to the other side. So your equation can look something like negative R over L dt is equal to I di, and all you really need to do is, well, sorry, not I di, 1 over I di. Now all you really need to do is integrate both sides, and this is quite simple. All you're going to get is negative R over L t plus c is equal to ln absolute value I. What you would need to do now is take the exponential so you can get an equation of t. So you get e to the negative R over L t plus c is equal to your ln I, your I. And basically you can rewrite this so that you have your e to the negative RL t multiplied by e to the power of c equals I. And your e to the power of c can basically be c1, so you can actually get rid of this. So you can have your final equation as c1 multiplied by e to the negative R over L t is your I of t. So that's your final equation right now. Now, an important thing to note would be try and solve for C1 now, since we have an initial condition right here. So what I'm going to do is actually erase all this over here, so we can go ahead and substitute our a substitute to find C1. So we're going to go ahead and substitute T star as your time. So you're going to get C1 is equal to e to the negative R over L T star. Oh, that's a horrible T star. So T star is equal to Vs over R. And what you're going to do now is actually divide both sides by e to the negative RLT star. So you get a C1 is equal, so you get your C1 to equal Vs over R multiplied by e to the power of R over L T star. Now what you can just go ahead and do is substitute this into this equation. So you're going to get something like Vs over R e R over L T star multiplied by e to the negative R over L T star, well, not T star, sorry, just T, is equal to your I of t. I'm just going to go ahead and erase this. And you can combine these two so you get something like Vs over R multiplied by e to the R L t star minus t is equal to your I to the t. Now something they've noted is that I'm just going to go ahead and erase this because they do want us to actually sketch this for you from t. We'll sketch it so we can combine the first sketch we've made and continue it with the second part of the equation when we flip the switch back to t star we split the switch back to 2 at a time as t star. Now one important thing to note would be your limit. Limit would be as t approaches infinity. Now as t approaches infinity, t is actually going to be significantly greater than t star. So what's going to happen is you're going to end up getting a negative number here. Basic example is a minus b, where b is greater than a means this is less than 0. So that's basically what's going to happen here. And any number, e to the power of any number that's really large, basically negative infinity, will in fact be 0. And you're going to get your it, so it to equal 0. So basically, at the end of this, t does approach, current does approach 0. So you can combine both graphs in a very simple way actually. Basically, the initial asymptote was Vs over R, which it does reach. So it basically goes to a certain, and continues for a while until you reach t star, after which it exponentially decreases since it's trying to reach your 0 mark. And that's basically your final answer for part B, and your final answer for the final question of T. You can add more points to this. I don't feel it's necessary, but again, it's best to ask TAs or profs, but this is your final answer right here. This is your equation. I know in the solutions, by the way, just a quick note, I know in the solutions, what they have done is written as minus R over L, T minus T star. You could do both, you could do either, it doesn't really matter. It's the same exact thing. The reason they did that is to make it resemble the previous equation that we've done. I didn't do that here, but it shouldn't mean it shouldn't mean this answer's any more correct or incorrect than the previous answer. Anyway, so that's how you do assignment 1, part B, question 2, part B.